All right. Welcome back, everybody. So today we're gonna continue our discussion of algorithms and algorithm analysis. So this is the last part of the class. It's the most fun by far. We get to use the skills and abilities we've built up, the knowledge about imperative programming and object-oriented programming to do some cool things. So that's kind of what we're gonna do throughout the rest of the semester. We'll learn some new things along the way. We'll add a few object-oriented concepts and techniques to our bag of tricks. We'll also learn about recursion, which is a new problem-solving technique that we haven't talked about yet. But, you know, a lot of what we're gonna do is think about algorithms, how to analyze them, data structures, how to build them, and really, I should say, how to analyze both, right? How to analyze data structures, how to analyze algorithms. So, as a reminder from last time and earlier in this semester, so, you know, and again, I think this is really important to understand. An algorithm is a set of steps that you can use to solve a problem. Algorithms need to be, you know, in a form where you can write them down. So, you know, you need to be able to describe how to solve the problem in some way that someone else could then use to either solve the problem or implement the algorithm in actual computer code. But the algorithm is not the code. The algorithm can be implemented in a variety of different ways. Sometimes you'll see algorithms written down in something called pseudocode. Pseudocode isn't actually real code. There's no compiler or computer program that can run that pseudocode, but it's specific enough that somebody could then take it and implement it in Java or Kotlin or Python or Ruby or Rust or whatever. Okay. And as computer scientists, you know, we are gonna utilize these computer capabilities to implement our algorithms. So we're going to perform simple computations. This is stuff that we talked about like the first couple weeks of class. We've been using ever since. We slowed down a little bit during the object section, but we're gonna go back to, you know, thinking about performing simple calculation, using variables to store the results, you know, repeating things over and over, and making simple decisions. Those are the building blocks for the algorithms that we're gonna talk about. So data structures, you know, so algorithms sort of connect back to the first part of the class. Data structures connect more to the second part of the class, right? Where we're finding new ways to structure data. We looked at arrays, we talked about arrays with the first data structure, and so far the only one, although today we're going to start talking about a generalization of arrays that we'll use to both build a cool data structure, learn a little bit more about Java, and get some practice analyzing algorithms. So as programmers, as Java programmers, if we want to structure data in new ways, one of the things that we have now in our bag of tricks is that we can extend Java's built-in class system. So we can create new kinds of data, using the classes that we've been practicing with, right? That's what they're for, right? One of the things they're for is to create new data structures. So we're gonna utilize that capability. We can also, you know, we'll also need to go back sometimes and store things in actual arrays. So the data structure that Java gives to us in today's homework problem, and on Friday we're gonna talk about how to use an array as the building block to build a more general data structure that acts like an array but has some features that arrays don't have that we would like. The ability to extend, you know, by adding items to the end or to the beginning, the ability to add items to the middle. These are things that if you programmed in Python or other languages that have built-in support for this, you've gotten used to. Java arrays don't do that, but we can build a data structure that acts like a Python list on top of a Java array. So our data structure is gonna store its data internally in an array, but it's gonna provide an interface that allows it to behave like a list. That's what's kinda neat. All right, and then when we look at our second array list implementation, so lists are like a great way to start this whole project, right? Because not only can we build them using arrays, which is the data structure that we already know about, but we can also build them by utilizing object references. And that's something that we're gonna then use to bootstrap our discussion of trees, right? So that's another way to establish structure between data, is to take two objects, two instances of a class, and have one of them or both of them store references to each other. So now we're creating structure between those pieces of data. All right. And again, these two topics are highly complementary, so this is really the part of the class where we're gonna interweave this as much as possible. So, you know, today and Friday, what we're really doing is building a data structure, a new data structure called a list. but we're gonna analyze some of the operations on a list as if they were algorithms. How long does it take to add an item to a list? How long does it take to go through all the items in the list? How long does it take to add an item at the end of the list? Things like that. We're gonna analyze those like they're algorithms. We're also gonna implement algorithms, utilize specific features of data structures, right? So a lot of times, you know, all the recursive algorithms that we talk about, almost all of them are gonna implement it on trees, because trees lend themselves very well to this type of algorithm and this style of programming. So, you know, we don't use data structures arbitrarily, we use data structures to achieve a result, which is typically that there's an algorithm that we want to implement that we can now implement because we've chosen to structure the data a little bit differently. And, you know, again, when we talk about trees, we're gonna talk about tree data structures first, and then we'll talk about the cool algorithms that we can use to build on top of them. But this is, you know, again, there's a deep relationship between these two topics. Neither one of them exists in a vacuum. They're really very much intertwined. Okay, and again, along the way, we get plenty of chance to practice with both imperative programming techniques that we learned in the first third of the class and the object-oriented stuff we've been learning recently. All right, so, as a review from Monday, when we talk about algorithms, one of the most important things that we usually want to understand about them is how they perform. So here's the thing. You know, you guys have been born into a world that is filled with algorithms. You know, if you look up how to sort data, you go to the Wikipedia page, you're gonna find a list of like 30 or 40 different sorting algorithms. These are different sets of steps to solve the same problem that have different trade-offs. So that's the trick. So if you just wanna sort something, you can implement BOGO sort. Does anyone know what BOGO sort is? Okay, a few of the sorting fanatics here have some sense of that is. You can implement BOGO sort. Your program will be very slow. Once you guys figure out what BOGO sort is, hopefully you'll get a little chuckle out of this. You can implement BOGO sort. It will work. It will eventually sort data. It's not very good at it. In fact, it's extremely bad at it. But it is a series of steps that will accomplish the result. As a sophisticated computer scientist, however, what you would do is you would look through that list, you would think a little bit about the properties of the specific data that you're trying to sort, and you would choose a different algorithm. Because BOGO sort doesn't perform very well, and there are sorting algorithms that do better. Okay, so the ability to think about, not just implement. Okay, so, you know, any hacker can implement an algorithm. A computer scientist can think about an algorithm and analyze it. They can think about what happens on different types of inputs. They can think about how it would work in different scenarios. Is it really good enough to solve this problem? These type of choices really matter, right? You know, this type of choice down the line for you might determine whether or not you get to keep a job, whether or not you get a job in the first place, whether or not your startup makes it big. You know, you guys don't really remember this, right? How many people remember a social network other than Facebook? Yeah, if you're embarrassed by your age, you don't have to raise your hand, but there's a few of us out there, right? You know, contrary to popular belief, Facebook was not the only social network. In fact, it wasn't even the first. Anyone remember any of Facebook's contemporaries? The old people out there? MySpace? Oh yeah, whew. Man, has anyone ever seen MySpace before? So I think MySpace was actually like a covert project to get all of the terrible web pages, really ugly web pages into one place. You know, so then we can kill them all off at once, right? Yeah, MySpace. What else? MySpace actually didn't really try to offer some of the features Facebook did. Yeah, AOL was like, yeah, okay, I'll take that. But something that was really trying to do something similar to Facebook, where you could go on and identify friends and stuff like that. There's actually a name for this. Friendster. Anyone remember Friendster? Anyone have a Friendster account back in the day? Yeah, I did. It's pre-Facebook. It was a social network that was out there. Do you know one of the things that doomed Friendster? I mean, Friendster worked, kind of. Like, you got on, you could see other people's profiles. It was kind of like an early version of Facebook. I mean, it never had the news feed. It never evolved because it died off pretty quickly. Do you know one of the problems Friendster had? Facebook didn't, at least initially? Related to what we're talking about. Just from a user perspective, yeah. It was slow. Yeah, it was slow. You go on, a page would take like a while to load. And my understanding, again, I never worked at Friendster, and hopefully someone that worked at Friendster will notice this and then flame me and I'll find out what really happened, right? But my understanding was Friendster was actually trying to maintain this social graph in real time. So so for example, if you, and they had these rules like, if you were 3 people removed from somebody, you were allowed to see their profile. Well, imagine as people are using this, some of you are probably on Facebook right now. You're like, oh, there he goes on another tangent. He's not gonna change the slides for a few minutes, so I'm gonna go check my newsfeed, right? But imagine as this graph is changing all the time, Friendster constantly has to be able to answer these questions about whether or not I can see somebody else's profile. So part of what doomed them, I think, from my perspective as a user, was that their site was slow, and I think it was just because they were trying to solve a really hard problem. Facebook didn't do this initially. Facebook got there eventually, but early versions of Facebook were siloed to specific schools that you were a part of. So you had certain permissions allowed you to see pretty much everything that went on at like your college, and very little that went on anywhere else. And that user model worked for a while for Facebook to help them get off the ground. So again, this stuff matters. If you go out and start a startup, and at the core of your business model is solving some unsolvable problem, you may not get very far if you don't have a clever way to do it. Okay, when we talk about algorithms, typically what we're going to focus on is what we refer to as the behavior at the limit. So what happens as the problem gets really big? What category does it come into? And there's a couple reasons for this. You know, one of the reasons is that that's when things get interesting, right? When the problem gets really big, that's when things will slow down and might become a problem. So we'll start answer questions like, you know, given certain inputs, in general cases, how is the algorithm gonna perform? So what's the best case scenario for the algorithm? What's the worst case scenario? But the number one thing that we're always trying to figure out is what's the relationship between an algorithm's performance and the problem that it's trying to solve, okay? So for example, if I'm sorting things, then you would expect there to be a relationship between how many things I have to sort and how long the algorithm takes. And sure enough, there is. If I'm searching for something, let's say I have to search through a bunch of items, again, you would expect there to be a relationship between the number of items I have to search and how long it takes me to find the item or to figure out that the item doesn't exist, right? So this is one of the things that we're gonna try to do. The notation that we use to put things into categories. So, and a lot of what we're gonna do, this is a very gentle, simple introduction into algorithm analysis. You guys will see more of this in 173 and way more of it in 225 and then down the line in 374 and other classes. So this is an important enough concept that we teach it to you over and over again. So this is just a gentle introduction. The notation that we use here is sometimes referred to as big O notation, okay? And it's essentially putting things into categories that are defined by the relationship between the size of the problem and how long the algorithm takes to solve it. And today, we're gonna go through those categories one by one and not only talk about certain problems that might have that property, but also look at some features of actual Java code that could give you a hint that you're dealing with a problem of that type. So here are our categories, shown graphically. So, and this is why this matters, right? So, ON is sometimes referred to as linear time. That means as the problem gets bigger, the algorithm gets slower. But it gets slower linearly as the problem gets bigger. So if you give me twice as many items to look through, my search algorithm takes twice as long, right? So that's down here. That's the green line. Oh, I have a little friend here helping me out. I wonder if I could like zap it with a laser and it would actually, I don't know, it's probably not that powerful. All right, so let's look at a different one that we're gonna look at today. So this is O(n) squared. So this is now polynomial time with 2 as the exponent. This means if the problem gets twice as big, the algorithm now takes 4 times as long. The problem gets 10 times bigger, the algorithm takes 100 times longer, okay? So this is bad. Then let's look even farther up here. So now 2 to the n. This is exponential time. The size of the problem is no longer the bottom part of the exponential, it's the exponent, okay? So now, as the problem gets bigger, the solution is slowing down even faster, right? So you can compare these two to each other, polynomial time and exponential time. And then way over there on the left, I have factorial time, which is awful. One of the algorithms, though, that I mentioned earlier, Bogo's sort, actually runs in factorial time. It's not good. It's not a good algorithm to use. You know, and then there's some other categories here, particularly the ones that have a logarithm in them, that are not gonna make a huge amount of sense to us until we talk about recursion, okay? But these typically have these typically occur when we have certain features of the problem where we can make it half as big. So searching through a phone book, for example, you know, this is the famous demo that David Malin does in CS50 every year. Take a phone book, I'm looking for a number, what do? I open it to the middle, and then I say, is the number I'm looking for in the first half or the second half of the phone book? And now I've made the problem half as big. So essentially, I only have half as many numbers to look through, and then I repeat that process. So no matter how big the problem was, if at every stage I can make it half as big, then I'm gonna be in what's called log n time, which is down here. And you can see log n time's pretty good. You can barely see it. It's barely growing as the problem size gets bigger. That's actually a really nice way to approach this. When I heard about that example that David does, it was like, oh, he's ripping a phone book in half. I thought he was ripping it in half like the hard way, you know, like across the spine. I was like, wow, he must have been working out since I knew him in graduate school. But he's ripping it like down the spine. That's easy to do, right? I always thought it'd be fun to do that example like with a chainsaw where we actually could like, you know, cut it the hard way. But that algorithm doesn't work very well either. All right, so here are our complexity classes. Now let's start meeting them one by one. Okay, now this one you don't even see here. Well, actually, it's on the graph, but you can't see it because it's hidden by the axis. So O1. Now one thing I want to point out here is that this is the only time that n does not appear in my big O notation. Sometimes you'll see this as OC. You know, the idea here is that these algorithms do not depend on the size of the input. They always take the same amount of time. You have algorithms like that, right? Imagine you give me any number of balls and I have to pick one at random. It takes constant time, I just grab one. I don't have to look through them all, I just take one at random. So, this is called constant time. This is not very common. So if you think about looking for something, if you think about sorting, if you think about, you know, some of the algorithms we've talked about, like designing a route across the United States to try to minimize travel time, these don't run in constant time. But sometimes we have algorithms that do run in constant time. And you know, these operations, these kinds of operations in Java do take constant time. So here's an example. Accessing an element from an array in Java takes constant time. One of the reasons why it's important to understand even something like constant time that's not that useful is that this is a building block for other algorithms. So if I have a loop that has something that is constant time inside of it, then I can be assured that my loop, you know, that the inner part of the loop takes the same amount of time every time I execute it, and now I can think about the complexity of the whole loop rather than just the inside part. Okay. All right. So now let's talk about where things start to get interesting. So ON. This is sometimes known as linear time. Here, the problem grows linearly. The amount of time it takes to solve the problem grows linearly with the size of the problem. And remember, part of our big O analysis is actually figuring out what n is. So depending on the problem, the first thing we have to do frequently is figure out what is n, right? What is the thing about the problem that we're measuring that we're then connecting with how long the solution is going to take. So if you imagine that I have a problem of size n and my algorithm needs to take a time that's proportional to the size of the input, one of the features that you're gonna see a lot here, particularly in code that we look at, is a loop, right? If I have an array of size n, and I need to go through every element in that array, I have an ON, that's an ON step, right? So essentially, here's my array. In this case, it's the size 1024. And imagine I'm going through and I'm computing a sum, right? So I set my sum to 0. This is constant time. And then I have this array here, I have this loop where I'm going through every value in the array. And I'm just adding it to my sum. This, I'll get to your question in a sec. This is an example of an ON algorithm. And you know, here's the way to think about it. Can anyone, if you guys can come up with an algorithm that can sum the elements in an array without reading every element in the array, then there is definitely some prize waiting for you somewhere, right? In a lot of cases, ON is the best that we can do because I have to look at every value. I can't compute, like if I wanted to sum all of your ages, I can't compute that without asking every one of you your age. I could estimate it, I could, you know, sample this area over here and then multiply by the size of the room, but that's not, now I'm solving a different problem, right? If I really want to know exactly what the sum of all your ages is, I have to ask every one of you your age. I can't do it without, you know, getting to everybody. Question? Is there a difference from our perspective between the enhanced for loop and the regular for loop for algorithm analysis? No. Yeah. No, so so the question was, you know, if I replace this with the regular for loop, or the index for loop, maybe is what we should call it, does that change the algorithm complexity? No, right? Still have to go through every value. Yeah. All right, so whenever I need to see everything, whenever I have a group of elements, and you might think about searching too, right? Let's say that I want to search through this room till I find somebody that has the same birthday that I do. Maybe there's nobody in this room that has the same birthday now. It turns out actually the probability that someone has the same birthday as me in here is really high. Like really high. Sometimes known as the birthday, actually sorry, no, I misstated it. The probability that two of you have the same birthday is like almost 100%. The probability that someone has the same birthday as me is lower than that. Right, we'll talk about this. This is known as the birthday paradox. But if I wanted to look through the room to find someone with the same, my birthday, again, it's possible I would have to go through everybody. Let's say I don't find anyone. I come over here, this side of the room, I go down, I work the entire floor, nobody has my birthday. I go up to the balcony, nobody has my birthday. I might have to talk to every one of you before I find someone that has my birthday. Now I'm curious, does anyone have my birthday? 9/15, any 9/15s in here? He claims, the people next to him are saying yes, and he's saying no. So someone is confused about somebody's birthday here, right? We can talk about that later. Anyway, but if I really want to make sure, I'd have to go through everything, right? So and a lot of search problems are ON. Particularly if I don't have the data organized in some way. When I have the data organized, I can do better than that. Okay. So again, and you can see already, we're seeing a pretty big difference between these two complexities. So here's ON, and O constant times down here, right? Okay. So what about this? Let's look at something more common. This is essentially a search algorithm, okay? I've got a value called looking for. This could be my birthday. And I'm going through the array, and if I find looking for, I'm gonna break, okay? So let's apply our algorithm analysis principles to this problem. And here, frequently, when we do this, it's helpful to think about best case, worst case first, okay? And then maybe you get to the average case. All right, so what's the worst case here? Let's start with the worst case scenario. Okay, yeah. Yeah, or it's not in there. Yeah, so essentially the worst case scenario is the array does not contain the element. Okay? Why is this the worst case scenario? Because in that case, I will never hit that break statement. And so I won't exit the loop until I've looked through every single value in the array. Okay? Okay, what's the best case scenario? Yeah. It's the first position. Yeah, bingo, okay? If it's in the first position, I have one iteration, okay? Okay, now this is where it gets tricky. Average case performance for this algorithm. Who wants to start me down a conversation about this? This is not as easy as you might think. Average case performance for this. Yeah. What's that? Square root of n? Okay, that's interesting. Can you explain your answer? Just sounded cool. Yeah, that's not bad. Not a bad reason. Anyone else wanna, what don't you know here that you need to know to answer this question? Yeah, so the distribution of the numbers in the array. Okay, so, let me make it easier. What if I know that the value looking for is in the array somewhere? I don't know where it is. I know it's in there somewhere. Then what is the average case performance? So I'm gonna find it. It might be the last element, it might be the first element, it might be anywhere in between. What's the average case performance? Yeah. N over 2. Sometimes it's right at the beginning. Other times, it's all the way to the end. But if I can guarantee that the element is in the array, then the average case is N over 2. But what if, okay, so what if the element is not in the array? Never in the array. What if the array is full of positive numbers and looking for is negative? Then what's the average case runtime? So now it's O(n), right? Because every time I go looking all the way through. So the thing that you don't know that prevents you from solving this, right? So best case first element, worst case last element, average case, I think the slide is wrong. It depends on the distribution of elements, right? If I know that looking for is in the array, then it's O(n) over 2. Now, when we talk about, one thing I want to point out here is that when we talk about complexity analysis, we typically just ignore multiplicative factors. So 2n, n over 2, n over 4, 8n, they're all O(n) to us. Doesn't matter. Just throw that out. Now, you know, again, if you work at Google and you go to your boss and you say, hey, I found an algorithm that makes search 8 times faster, you're still gonna get a raise for that, right? So don't be like, oh, it's still O(n), who cares, right? You know, I only made it 1,000,000 times slower, but it's still O(n), so like, no one cares, right? No, people care about that. But when we talk about categories of algorithms and growth, we're gonna ignore those factors, okay? Are they, you know, relevant in the real world? Absolutely, right? Are we gonna worry about them? Not so much. Okay, let's go on. O(n) squared. So now, again, the problem gets 10 times bigger, the solution runs 100 times slower. Problem gets twice as big, the solution runs 4 times slower. Here's a hint that you're looking at an O(n) squared problem. You see nested loops, right? So now, and if I had triply nested loops, I'd had O(n) cubed, right? Quadruplet nested O(n) to the 4th, right? So here's an example, okay? And this is also an example of a terrible algorithm. Remember I said, we talked about last time, you know, algorithms can move, a bad algorithm moves a problem from a faster complexity class to a slower complexity class. A good algorithm does the opposite. So this is a bad algorithm. We'll talk about it more in a minute, but you might start looking at it and figure out what it does, okay? So I'm taking, well, actually you could just read the name and figure out what it does, right? So this is called isSorted. It returns a Boolean. It takes an array of integers as input. It's so nice to look at some imperative code again, right? Kind of fun. I have 2 loops. My first loop goes through the array. My second loop goes through the array and it starts at I. Okay, so it's not actually going through every element. You know, it doesn't make that big of a difference here. And essentially what I'm looking for, I'm looking at pairs of elements. And I'm looking for a case where an element with a larger index is less than an element with a smaller index. So if I start at j at I and j goes up to array.length, j will always be equal to or bigger than I. I could really start j at I plus 1, but this is okay. So essentially I'm saying if I found a pair of elements where j is bigger than I, but array j is smaller than I, I'm gonna return false. Otherwise, if I go through the entire array and I don't find those elements, I'm gonna return true. So what is this doing? It's checking to see if the array is sorted. Right? It's one way of doing it. It's not a good way. All right, so in this case, I both have to loop and compare, and so in those cases, frequently I end up with something that has nested loops and ends up being O(n) squared. And again, you know, we're ignoring the constant factor here. This isn't exactly O(n) squared, because the first time I go through, I execute n. The second time I go through, I execute n minus 1, n minus 2, n minus 3. And so really this is, n, you know, n squared over 2. It's n for the outer loop, and n over 2 is an average for the inner loop, but who cares? We're gonna ignore the constant factor and call this O(n) squared, all right? And you can identify this frequently by these nested loops. Two loops on top of each other, where they're not nested, don't mean you have O(n) squared. There you might have like O2n, an O(n) step and an O(n) step, but that those add together, they don't multiply together. All right, so let's analyze this little algorithm. So what's the best case scenario? So now, again, we're thinking about inputs. I'm thinking, what I'm asking you is give me the input that causes this algorithm to perform well. Or tell me what kind of, in what kind of cases. There's actually an infinite number of inputs here where this algorithm will perform well. It'll take basically 1 or 2 steps. All right, what are those? Yeah. Well, remember, we're gonna normalize for the size of the array. So the answer was super small array, yeah. If you give me a small array, n is small, and the performance is small. But I'm saying even within n, right? This is actually true of any size array, right? There's a feature of the array that's gonna cause this algorithm to perform really well. Put it this way, if I give you an array with n elements in it, all you need to do is change the 2 elements in that array, and you can cause this algorithm to do very well. Okay? What 2 elements are they, and what do you do? Yeah. Yeah, look, I've got an escape hatch here. I have a return statement in my inner loop. It's under a conditional, so the trick is, how do I get this algorithm to head down this path, okay? So let's think, you know, okay, so the first time I come through here, I is 0 and j is 0. Now, array I and array j are gonna be the same at that point, so I'm never gonna get into the conditional on the first time through, okay? If I started this at I plus 1, I could, but I started at I, right? If I and j are the same, then array j is never less than array I. They're the same value. But the next time I go through the array, my inner loop, j is now 1 and I is 0. So if the second element of the array is smaller than the first element, I'll return false. Every time. The rest of this doesn't even execute, remember? Little review about how functions work. As soon as I hit a return statement, I'm done. Bail out, go home. So I can you can run this on an array with 1 billion elements, but if the first one is 1 and the second one is 0, it is finished. It has found what it needs to find. Because it's looking for whether it's sorted in ascending order, and if the first element's 1 and the second element is 0, well, clearly it doesn't matter what happens to the rest of the array. I've already found a counterexample that the array is sorted. Okay, so the best case is that the unsorted pair is right at the very beginning. In that case, this algorithm will never take more than 2 steps. What is the worst case for this algorithm? This is kind of interesting, yeah. Yeah, that it's sorted, right? So imagine it's sorted in ascending order. Then what's gonna happen is, I'm never gonna get into this loop, into this return statement, excuse me. I'll never get into this conditional, okay? And so I won't return until I get here, which means that I dropped out of my outer loop, and that means that I executed my inner loop every time. There's no break, right? The only way that I escape here is through this conditional that starts on line 4. All right, so the worst case here is if the array is sorted. And this is actually an interesting example of a type of algorithm that you see. This algorithm tries to find out whether the array is sorted by finding a counterexample. And so if the array is sorted, it's gonna return true, but it only returns true at the very bottom. And so in certain cases, like, let's say that you have let's say as part of your program, you need to check to make sure an array is sorted. You're pretty sure it is sorted. This might be like part of a testing code that you run that just makes sure the array is sorted before you render a list of elements to the user or something like that. Now your verification step takes O(n) squared every time you run it, even if you think the data's already sorted. So that's kind of not a great, great property, okay? So, and again, if I don't know where the element is that is unsorted, it could be at the beginning, it could be at the end, the average case performance of this algorithm is O(n) squared, okay? Because essentially the pair of elements could be anywhere in the array. So now we're up here. We're looking at an O(n) squared algorithm, right? These are where things start to get bad, you know, where we start to worry about performance, particularly as the problem gets big. So this is one of those cases where if you ran this on your local machine and you gave it an array with 5, 10, you know, someone pointed out small arrays always do good. Yeah, so if my test cases all have arrays of size 4 and 8 and 12 or whatever, because those are the ones that I could write down for the test, then I'm good. But now I'm running this in production and I have an array with 1 million elements and, you know, my coworkers are like, dude, the server's down. And you're like, no, it's not, just running my sorting algorithm, right? No problem. Just give it 10 minutes and it'll come back up. I'm sure nobody will notice. All right. As I pointed out before, I'm not gonna talk about these growth rates very much. We'll come back and get these, because the logarithmic part of these has to do with this, again, this feature of making the problem, dividing the problem in half, right? But essentially the way you can think about it is that if I have an algorithm that can make the problem half as small in every step, then I have usually either O log n or O(n) log n runtime, okay? All right, and the recursive algorithms that we'll start to implement on trees frequently have this problem. Okay, so now let me come back and, you know, try to make this relevant for you again before we spend a few minutes talking about lists. So, you know, remember, a dumb algorithm makes a simple problem harder, okay? So, the test that we wrote to see if an array is sorted is dumb. That is an O(n) problem, okay? So again, I sometimes have wished in the past that I could have some sort of special, like, slide background that I use when I show you bad code. But if I did, I would use it right here. Do not reproduce this algorithm. It's wrong. There is a much faster way to find whether an array is sorted. So this is a dumb algorithm that has taken an O(n) problem and made it O(n) squared. On the other hand, smart algorithms can take a problem that you could solve, you know, maybe using a brute force solution in a certain way like we did with GCD, right? So our GCD algorithm was O(n), the Euclid's method is O log n. So now we've taken a problem that the straightforward solution was, you know, ran in linear time, but actually, sorry, it was O(n) squared, right? And we can actually take that down to O(n) log n. And that makes a difference, right? So again, my sorting algorithm, my isSorted method, took a problem that belonged here and moved it up here. And Euclid's method took our algorithm that started here and moved it down here. Okay. So, you know, since this is an introduction to computer science, I always find it fun to get to this moment, right? So, you know, again, I wanna make sure that you guys don't exit this class without a sense that there are deep, interesting, unsolved problems in computer science. How many people have heard about this problem before? Okay, so a few of you, okay? And the way that we refer to this problem is, you know, the P-NP problem. That's how you'll hear people talk about it. P versus NP, or does P equal NP? And I am not going to talk about this at length. But what this problem is really about is hardness, difficulty, algorithmic difficulty. So essentially, there's something about the world that we don't know, okay? We don't know if there's a specific category of problems, and we've identified lots of problems that fall into this category, and it turns out they're all related to each other, which is also really interesting, right? But right now, it seems that there's a specific category of problems in the world that are harder than every other problem that we know about, okay? Those problems are in this category called NP, non-polynomial time. They are slow to solve. Everything else is in P. So pretty much every other problem you can think of, we've managed to find a polynomial time algorithm for, right? So again, let's go back here, right? So what is a polynomial time algorithm? A polynomial time algorithm is something that could be n squared, it could be n to the fourth, it could be n to the 12th, it doesn't matter, okay? Non-polynomial is the stuff to the left, right? Things that grow faster than every polynomial. So this is, you know, again, and I don't know, I'll be really curious whether in your lifetime you will see somebody prove this. Now, over time, we have developed a little bit more confidence about this because no one has been able to find a polynomial time algorithm to solve certain problems. And the thing that's interesting is that so remember I said there's this like group of problems that are all similar. So actually, there's a group of problems where if you solve one of them, you'll solve all of them, right? The one I'm gonna show you is in that group. There's a group of similar problems where I can take a solution for one and use it to create a solution for any of the others. We have not managed to find a polynomial time algorithm to solve any of those problems, okay? The problems that aren't in that group, we have found polynomial time algorithms for. So does anyone, this happened maybe in the last 10 years. Does anyone remember there was kind of a big announcement about one problem that we had thought was in NP, somebody came up with a polynomial time algorithm for it. Does anyone remember what that problem is? Super relevant to online security and all sorts of other interesting things. Anyone remember what problem that was? You guys were alive when this happened. It was not that long. Factorization. So, given a number, figuring out all of its factors, right? And essentially testing if it's prime. I think the problem was called prime. Given a number, testing whether or not it's prime. We used to think that problem was in NP. Now it turns out that we found a polynomial time algorithm. Now the polynomial time algorithm that we found still doesn't get used a lot because it turns out that it's slower than the best non-polynomial time algorithms that use randomness to attack the problem in a way that's really cool. All right, so here's an example. Now here's the thing that's interesting about this category of problems, these non-polynomial problems. It's not just that they're hard, it's that it's also easy to verify a solution. And Sudoku's a good example of this. So Sudoku turns out to be an example of a problem that is what's called NP hard, or NP complete. But, if I give you a Sudoku puzzle and ask you to verify that I've solved it correctly, you can do that in polynomial time. So there's two things that have to be true. I have to be able to verify the solution very quickly, but coming up with the solution is very difficult. Now it turns out for small grids, Sudoku is actually pretty easy, but if you make really big Sudoku puzzles, they get hard extremely quickly. All right, I'm actually gonna, well, you know what, I can get through this in 2 minutes. All right, total change of topic very quickly because it's something that we need to talk about in order to talk about the container data structures we're about to get to. I apologize for that. It's like a total train wreck transition right there. Okay, so remember we had those primitive types? Like the primitive types, int, long, stuff like that. So those turn out to be annoying at this point in our life. Everything else in Java is an object. And objects have these methods like hash code and equals. And we want to be able to use those methods sometimes, but we still want to be able to work with things that are like integers, longs, and stuff like that. And so Java provides what are called wrapper types, okay? So here's an example. Now you see something that looks like creating an object, but it takes an integer literal, okay? And for every single, this is a super exciting slide, get ready. For every single primitive type, there is a wrapper type. The wrapper types are objects. They start with a capital letter. Usually they share a similar or the same name as the primitive type that they wrap. So again, 8 primitive types, 8 Java wrapper types. I'm doing this because we're gonna start using these, okay, when we talk about lists. Okay, yeah, super exciting. Okay, I'm glad I got that out. All right, so I'm gonna go through this quickly because partly you guys need this for today's homework, right? And the next couple homeworks you guys are gonna do. So what we're gonna start to build together and this is a great chance to both talk about data structure design and algorithm trade-offs, is something called a list, right? A list is a generalization of an array. So just like an array, a list puts items into order, okay? And it has features that are similar to an array. So for example, you can get and set values in the list, just like you get and set values in an array. Now, to do that, you use a get and set function. You don't use bracket notation, but the list provides that function for you. However, like I said, this is a generalization of an array. It has some new features that we want. I can add and remove values anywhere in the list, at the front, at the back, in the middle, okay? So lists are probably one of the two most useful data structures that you will meet as a computer scientist. Sometimes I refer to these as the data structures that you meet in heaven. Lists, maps. We'll get to both by the end of the semester. Lists are the first one that we're gonna talk to, okay? We're gonna implement two different types of lists together, both in class over the next couple of lessons and also on the homework problems, okay? And the reason why we're doing this is a great chance to show you the trade-offs between two different ways of implementing the same interface. I also use the word interface, right? Because lists provide an interface that allows them to behave the same even if they are implemented differently. So lists are our first example of this, okay? And so we're gonna look at an example of a list built on top of an array, and then we're gonna build something called a linked list that uses object references to store the structure of the list. All right, so Java lists are a real thing. There are already lists implemented in Java. We're gonna have you guys work with a simplified version of the list interface that I'm providing right here, okay? So this is the interface that your list that you start working with today on the homework and will continue working with next week is going to implement. We're gonna get to the point where we have two different implementations of this interface. One's gonna be called a simple array list, the other one's gonna be called a simple linked list. The reason why we're not using Java's list interface is because it has a bunch of stuff in there that we don't care about. So this is it, okay? Get and set work the way you would expect them. These are very similar to just using the array bracket notation. Add is something new. That actually increases the size of the list by 1. Remove decreases the size of the list by 1. And then we also have a size method. All right, this is where we'll pick up on Friday. I have office hours today from 1 to 3. Please clear the room quickly today. The class after us has a midterm. I will see you guys on Friday.